3i Atlas is moving closer to the sun. There's still so much we don't know, and with the sun's glare taking over our window to see this interstellar visitor from Earth.
Astronomers expected a routine flyby. Instead, 3i Atlas flashed an intense, focused beam, aimed not into deep space, but straight toward Mars. Spectra went weird. Brightness spiked and crashed, colors flipped like a cosmic mood ring, and then the light aligned, deliberate, precise, unsettling. Is this a freak of physics, or something planned? Why does its path skim the planet's plane with needlepoint accuracy? And what happens if Earth is next in line? Today, we pull apart the data, the claims, and the wild possibilities, without jumping to conclusions. Because what's coming up may be stranger than the headline. When comets don't behave. For most astronomers, comets are predictable guests. They follow long, graceful arcs around the sun, warming up as they approach, shedding gas and dust in a steady rhythm, and glowing with a brightness that can be charted months or even years in advance. They are the dirty snowballs of space, beautiful but ordinary. That's why 3i/ATLAS has thrown the rulebook out the window. From the moment it was spotted, it began doing things no comet is supposed to do, forcing experts to question whether they were even looking at a comet at all. The first anomaly came in its brightness. Normally, comets brighten gradually as their icy surfaces heat and vent gas. With 3i/ATLAS, the change was abrupt and erratic. One night, telescopes captured it at a faint 18th magnitude, making it nearly invisible against the dark sky. Next, it exploded to 12th magnitude, bright enough for mid-range observatories to track. Then, just as suddenly, it faded again. These wild swings repeated over and over, sometimes in less than 24 hours, leaving astronomers scratching their heads. Expensive instruments were recalibrated, tested and retested, but the culprit was not broken gear. It was the comet itself, behaving like a cosmic strobe light. That wasn't the only surprise. With most comets, the glow originates from a diffuse cloud, known as the coma, that surrounds the nucleus as ices vaporize. But early observations of 3i/ATLAS suggested its light was coming directly from the surface. This wasn't a fuzzy halo, it was a pinpoint glow, as if the object itself was generating light. For scientists accustomed to comets behaving like passive reflectors of sunlight, this was like stumbling on a snowball that somehow makes its own fire. Now came the color shift. Many comets changing color gradually as the solar heat induced the sublimation of different molecules that fluoresce. This process is well documented. Reds, blues and greens appear at expected distances from the sun. But with 3i/ATLAS, impatience set in. The shift from red shades to green was accomplished so much quicker than physics allowed, well before entering regions where carbon compounds normally would trigger that type of change. It was as if the object had tantalizingly skipped ahead in the playbook, broadcasting signals in hues not yet able to be called on. For scientists, each of these anomalies raised troubling questions. Were the brightness irregularities associated with some exotic chemistry, or is it something deeper and possibly an internal energy release? Was the surface glow a signature of some exotic dust, or did it hint at a reflective or engineered surface? And what of the color change? Was that the signature of something we've never catalogued, or is it suggestive of a process outside our models of cometary behavior? As the nights continued to pass until that date, and the numbers appeared to pile on, it became ever clearer that 3i/ATLAS was not going to comply with neat, predictable-looking equations. Its behavior seemed more like that of the rebellious teenager of the solar system, acting as if it had been given a free pass not to follow every rule that was laid down in 4 billion years of comet observations. Every spike, every fade, every unnatural jerk took astronomers that much closer to the realization that they were either being privileged witnesses to a new class of object, or, really, something masquerading as one. And yet, that was only the warm-up act. For brightness tantrums and color tricks, the next feature violated a law of physics that any student learns in Astronomy 101, the direction of the tail of a comet. What 3I/ATLAS did with its tail wasn't just unusual, it was impossible. The forward beam paradox. Every comet has one rule carved into stone. Its tail always points away from the sun. Solar wind and radiation pressure push dust and ionized gas outward, like a cosmic windsock showing the flow of stellar particles. It doesn't matter how the comet spins, how big it is, or what it's made of. Physics guarantees the tail streams in the same direction. But 3I/ATLAS, it seems, didn't read the manual. Images captured by telescopes showed something nobody expected: a narrow, forward-pointing structure. Instead of trailing behind, this beam of light extended toward the sun itself, as though the object were shining a spotlight straight into the glare. Astronomers scrambled to explain it. Was it an anti-tail? A known but rare phenomenon where geometry creates the illusion of a forward spike. Normally, anti-tails appear faint and fleeting, visible only under specific alignments, when Earth, the comet, and the sun line up just right. But this was different. The structure was bright, long, and, most unsettling of all, stable. For days, the beam held its form, reaching 10 times farther than any anti-tail ever recorded. Its intensity rivaled the normal tail itself. Instead of a diffuse glow, it looked concentrated, almost focused, like a flashlight cutting through space. Natural processes scatter light in all directions. Nothing in physics should allow a comet to produce a directional beam that holds its shape over vast distances. Yet there it was, etched into the data. Scientists tried their best to salvage the explanation, applying dust mechanics. Perhaps unusually large fragments had shed and drifted ahead, strangely scattering sunlight. However, that was still something of a stretch. The solar wind should have pushed those chunks behind. For them to remain forward, they should have withstood those forces that dominate comet dynamics, measured and corroborated innumerable times over by the entire solar system. The odds were getting really thin. Others claimed electromagnetic effects. Could charged particles have been shipped around some invisible magnetic field, producing the illusion of a forward stream? The trouble was this: no comet has yet shown such behavior at this scale, plus magnetic fields strong enough to affect such behavior should be detected. The math also stood firm against them. Thus, then, commenced the whispered conversations. If the beam was not a command tail, was it a signal? Was the tightly focused forward light somehow intentional, for example, by way of directed energy, communication, or propulsion? Most chose not to articulate it, but the question was almost tangible. An anti-tail that points toward the sun is like having water run uphill, or fire that is cool. It breaks just too many laws that the explanations start to tiptoe into the realm of science fiction. The forward beam was not just counterintuitive, it became a choice. Accept that nature has hidden a trick we may still not have figured out, or entertain the unsettling idea that perhaps something, or someone, was guiding this light, and if the beam raised eyebrows, the chemistry raised alarm. Because what 3I/ATLAS is made of doesn't fit into any known category of comet, or any natural object at all. Chemistry that shouldn't mix. When astronomers trained spectroscopes on 3I/ATLAS, they expected the usual dirty snowball recipe, mostly water ice, dust, carbon monoxide, and the occasional organic trace. What they found instead looked like someone had taken the periodic table, shuffled it, and dealt the cards at random. The readings suggested a bizarre blend: about 87% carbon dioxide, 9% carbon monoxide, and a meager 4% water. That's not just unusual, it's upside down. In every other comet studied, water dominates. It's the driver of outgassing, the source of a glowing coma, the foundation of their icy bodies. Strip away the water, and the physics of comet activity collapses. Yet here was 3I/ATLAS, behaving wildly, while carrying almost none of the ingredients comets are supposed to run on. Then came the real kicker: nickel without iron. In natural cosmic environments, nickel and iron are inseparable twins. They form together in stars, fuse in supernovae, and land together in meteorites. To find nickel in isolation is like finding salt without chlorine or oxygen without hydrogen. It doesn't happen in nature. But 3I/ATLAS didn't seem to care. Its spectral fingerprint revealed nickel standing alone, with little to no iron to accompany it. Planetary scientists considered this a chemical crime scene. How could these materials coexist in such concentrations? If formed in an entirely different planetary nursery, the proportions must arrange themselves according to common rules of element formation. To explain 3I/ATLAS, you would have to conjure an environment where carbon dioxide was as common as sand, where nickel condensed alone, and where water, abundant everywhere else, was scarce. Either this object then comes from a totally different system, or else these materials were somehow manufactured or separated. The mixing of weird ingredients did not stop there. Trace compositions were the fuel to the fire, the exotic molecular lines not matching common cometary volatiles, and hints of unstable structures that should have already fallen apart long ago, drifting through interstellar space toward our solar system. Each measurement forced the screws of mystery tighter. If this were indeed a comet, it was a comet that was not made right. Skepticism encouraged caution, they said. The information was scanty, gathered in tough conditions for observation under conditions that muffled noise. Misinterpretation could give rise to results very strange. Still, this pattern was consistent enough across instruments to make such a view difficult. There was even evidence of solidity within margins of error so softened that percentages could be considered extreme for defense. The two options that remain were either 3I/ATLAS, being a natural body from an alien system with such a chemistry beyond our templates, or it is nevertheless something else designed or altered object to contain materials we would not have expected. Neither answer is tenable. One forces us to rethink how planetary systems can form. The other suggests intelligence had a hand in shaping what we're watching. For now, it has the spell of a riddle in the spectrum, but if chemistry raised the question of origin, its path through space advanced an even stranger question: intent. Because when astronomers traced 3I/ATLAS's trajectory, it didn't look random. It looked chosen. A path that feels planned. Interstellar visitors usually wander in on chaotic paths, swooping into the solar system at steep angles before disappearing back into the void. They don't care where the planets are. They don't hug the orbital plane. They certainly don't time their closest approaches for convenient observation. But 3I/ATLAS seems different, as though someone plotted its route on a star chart instead of letting chance decide. From the start, astronomers noticed its trajectory was unusually flat. Rather than cutting across the solar system at an odd tilt, it threaded almost perfectly along the same plane where Earth, Mars, and the other planets orbit. That's like throwing a dart from light years away and hitting a line thinner than a piece of paper. The probability of such precision occurring by accident is vanishingly small. For most interstellar comets, the odds say random. With 3I/ATLAS, the odds whisper guided. Then came the waypoints. Its path skimmed close enough to Mars for detailed study, but avoided Earth by a comfortable margin. That balance, near enough for curiosity, far enough for safety, looked eerily deliberate, and the timing added fuel to the fire. At its closest approach to the Sun, 3I/ATLAS would line up directly behind our star from Earth's perspective. To us, it would vanish into the glare, shielded from almost every telescope. Astronomers call this moment perihelion. Engineers might call it the perfect blind spot. Coincidence? Perhaps. But to many, it looked like a strategy. Hiding behind the Sun is exactly what a reconnaissance probe would do if it wanted maximum energy from solar radiation while minimizing its chances of being caught by prying eyes. The geometry felt less like luck and more like mission planning. Skeptics protested. They argued that sufficient numbers of such objects traveling from one star to another must lead to at least one object being on a course that would look deliberate to everyone. Probabilities have allowed for outliers. The universe is large, and sometimes chance can mirror intent. However, the combination's ecliptic alignment, Mars flyby, Earth avoidance, and solar concealment add up in ways that were hard to deny. The separate details could be explained away. Together, they were felt to be a pattern. That moment drew Harvard's astronomer Avi Loeb into the fray. Already much discussed in the context of arguing that Oumuamua, a former interstellar visitor, might have been man-made, he saw 3I/ATLAS potentially as an even more compelling candidate. It could be a sort of mothership, releasing smaller fragments, or probes along the way. The spikes in brightness, possible deployments, forward beam, or perhaps propulsion or communication directed outward, and the trajectory itself. Classic mission planning, just as human space agencies do when sending craft through planetary systems. Essentially, the critics brushed off that theory as especially unscientific. But the problems wouldn't just die. Too many anomalies were grazing in the vicinity at once. Even those on the fence about the object being of artificial origin would say that 3I/ATLAS does not fit cozily within any natural classification scheme. On the other hand, if it is natural, then 3I/ATLAS compels us to admit that we don't understand how interstellar chemistry and dynamics might be shaping these types of objects. Our comet model may need to be rewritten. If it's the only other option is an intelligent hand giving it a nudge, then we could be seeing the very first intentional flyby of Earth's neighborhood by something built in another world. But none of those are comforting, and all require urgent investigation. However, the matter remains open for discussion. One thing is for sure. The object is not finished with its act. Its path is deciphering itself in such a way that instruments on Mars may catch a glimpse Earth cannot. And that glimpse may be the one that reveals to us our lucky or intelligent design. And that brings us to the red planet, the one place with the best seat in the house to capture what 3I/ATLAS really is. Mars has the shot. For all the theories, debates, and heated arguments, the truth about 3I/ATLAS might not come from Earth at all. Instead, the clearest answers could arrive from the red planet. By sheer geometry, Mars happens to be in the perfect position during the object's closest approach. That alignment gives spacecraft orbiting Mars a chance to do what Earth-based telescopes cannot: get a direct, high-resolution look at the most puzzling visitor in modern astronomy. The timing couldn't be better. On October the 3rd, 2025, 3I/ATLAS will swing past Mars at a distance close enough for instruments like NASA's Mars Reconnaissance Orbiter (MRO) to capture detailed images. Its onboard high-rise camera, capable of resolving surface details down to about 30 centimeters per pixel from Martian orbit, might not show rivets or antennas, but it could reveal shape, structure, and light behavior with a clarity no Earth telescope can match. This would mark the first time in history that an interstellar object is imaged from the perspective of another planet. For astronomers, that fact alone makes this encounter historic. The scientific potential is enormous. If 3I/ATLAS is reflecting light in strange ways, MRO could confirm whether the beam is nothing more than an optical illusion caused by dust trails or geometry. If, however, the object is emitting light, Mars instruments might capture a spectral signature that doesn't align with ordinary reflection. That single detail, whether the light is reflected or generated, could determine if the beam belongs in the realm of physics we know, or if it points to something altogether more exotic. Even basic measurements would carry weight. A well-defined outline could reveal whether the body is spherical, irregular, or even geometric in ways natural processes rarely produce. A rotation rate could indicate stability or, strangely, maneuvering. Surface texture could hint at fractured rock, frozen gases, or something engineered. Every pixel matters when the object itself defies categories. Mars is not going it alone. Europe's Trace Gas Orbiter, India's Mangalyaan 2, and the Tianwen-1 mission from China can all help provide instruments for additional data gathering for triangulation. Measurement coordination across these platforms could well produce perspectives, datasets, and cross-confirmation. If 3I/A TLAS is a natural object, this collaboration will advance cometary science. If it is not, redundancy will then be critical. Cross-nation verified evidence is harder to dismiss. The urgency cannot be overstated. Interstellar visitors don't hang around. Instead of passing by every couple of decades like local comets, 3I/A TLAS is one way only. After the sun's slingshot maneuver, it will head back into deep space, likely never returning. One shot for humanity, miss it, and the mystery might remain forever hidden behind stars. Thus comes in an undercurrent of an intentionally more sinister tone. 3I/A TLAS could have chosen a deliberate flyby near Mars, stretching far beyond mere coincidence. Was the forward-pointing beam directed at the planet on purpose? How far does one conjecture? Is Mars a trial subject, a strike target, or expressly a switching relay for signals? Quite disturbing considerations, yet they walk alongside scientific excitement. Perhaps Mars is not only the optimum point of observation, it is the ordained one. For now, all the more eyes are turned towards the red planet. The orbiters are already set, timelines have been erected, and anticipation mounts. Images will soon replace speculation, but whether dust, ice, or design passes the camera lenses, one thing is evident: Earth will then have to come to grips with its meaning for us. If Mars sees us first, we might not be far behind. If a visitor can aim at Mars, our best answer is data, not panic. If you want the breakdowns the moment they drop, like, subscribe, and ring the bell. Comment your read: unknown physics, clever ice and dust, or a mission in plain sight. And when new frames arrive, tap the next video on your screen. We'll dissect what's real, what's noise, and what we still can't explain.